Yeehaw! We're going to have some fun. We're going to look at binary. This is PIC Computing, A-Level Computing, video number 19. Now, as humans, we count in something called decimal, or we might also know it as denary. And this is a base 10 number system. And you'll see why in a moment why we call it base 10. If we take the denary number 3126, we know that the 6 part means 6 ones. We know that the next part, the 2 part, means 2 lots of 10. We know that the 1 part means 1 lot of 100. And we know that the 3 part means 3 lots of 1000. We get the answer then by doing 3000 plus 100 plus 20 plus 6 equals 3126. This sort of thing will be nothing new to you. What we're going to put in the top row of this table now isn't essential to remember, but might help us understand binary when we look at that in a moment. 10 to the power of 0 equals 1. 10 to the power of 1 equals 10. 10 squared, or 10 to the power of 2, or 10 times 10, equals 100. So what I'm doing here is I'm putting the base 10 number system into place, and the exponent, or the power of, is raised by 1 each time. So the next one is 10 to the power of 3, or 10 cubed, or 10 times 10 times 10, and from that we get 1000. If we were going to do 10 to the power of 4, that would be 10,000. That's how the decimal or denary number system is built up. Now, like I say, it's not essential to remember how that bit works. It just might be handy for future. Now, poor old computers aren't very clever. They aren't very intelligent things. They can only understand something called binary, which is ones or zeros. If we were to store an audio file, an image file, a video file, or even a text message, all of these things are made up of a series of ones or zeros. On a RAM chip, a memory chip, there are millions of tiny little components, and each one of those components, or slots as I like to call them, can only store a 1 or a 0. So binary, ones or zeros, is a base 2 number system because there are 2 possible values within it. Every 1 or every 0 that is stored in a slot is known as a bit. The definition of a bit is a single unit of memory and can only store 2 possible binary values, either 0 or 1. So here's a big series of 1s and 0s. And us humans, if we had to program a computer, it would be difficult for us to remember what the series of 1s and 0s should be for different things. And this is why we invented programming languages. So this big set of 1s and 0s here, over here on the left, might be the equivalent of using a particular programming command. And because programming languages are a bit closer to English, they're easier for us to understand, so we can program computers and get them to do what we want to do without memorizing big sets of binary. So what you're going to need to know is how to convert a binary number into a denary number, or a decimal number, and back again. But we'll look at converting binary to decimal first of all. So the binary number that we're going to need to convert in this example is 10010101, and that is an 8-bit binary number because it's got 8 digits in it. First thing we're going to do is we're going to build up the binary number system. And the first number in the binary number system is 1, and that's because of our base 2 number system. 2 to the power of 0 equals 1. 2 to the power of anything to the power of 0 equals 1. 2 to the power of 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the power of 4 is 16. So that's 2 times 2 times 2 times 2. 2 to the power of 5 is 32. 2 to the power of 6 is 64. And 2 to the power of 7 is 128. Again, it's not important to remember this top row. It's much more important to remember the next row, because you will need that in any sort of conversion involving binary. You'll need to remember that sequence of numbers. So once we remember that sequence of numbers, the next thing that we do is we just write in our binary number, all 8 bits of it. And it doesn't really matter too much if you start from the right or the left in this example, because it's 8 bits and there are 8 slots. So we write that in, and then what we do next is we have a look and we see if there's a 1 underneath the first one, then we use 1 to 8 as part of our calculation. Anywhere there is a 0, we don't use the numbers above in our part of our calculation. So we're going to use 1 to 8, but we're not going to use 64 or 32. We are going to use 16 because there's 1 underneath it. We're not going to use 8. We're going to use 1. We're not going to use 2. And we're going to use 1 on the end here because there's a 1 underneath it. So we end up only using 1 to 8, 16, 4 and 1. We add all those together to get our answer of 149. I'm going to show you a little bit of an easier method, I think, and this is the way I prefer to do them. We can forget about our top row, like I said, and just get rid of that row. We are going to add another row into the table at the bottom, and we're just going to get rid of the binary for the last conversion that we did. And the binary number we're going to convert this time is 101010. But notice that this binary number only has 6 bits in it, and that will be relevant in a moment. What I'm also going to do for this example is just get rid of our binary number system there, and just try and give you a bit of an easier way to remember it. We know that it starts off on the right hand side with a 1, and all you've got to do each time is double the number. So 1 doubled is 2, 2 doubled is 4, 4 doubled is 8. We keep doubling each time till we end up with 128 over on the left hand side. Now, we said that this was only a 6-bit binary number. It's a good idea to format it by adding any leading zeros on the end, so we've actually got 8 bits. When I say add the leading zeros on, it's over on the left hand side. So 101010 is the same as 00101010, but this will just be easier to put into our grid above. So let's put it in. There it goes. And then what we said is if there's a 0 underneath the top numbers, then we don't use the top numbers. So I think just having another row below our binary digits here helps us to draw this out and visualize it and get our head around it. So we're not going to use the 128 because there's a 0 there, so we put in 0. We're not going to use the 64. We are going to use the 32 because of the 1 there. We're not going to use the 16. We're going to use the 8 because there's a 1 there. We're not going to use the 4, so we put 0. We're going to use the 2, so we put 2. We're not going to use the 1 because of the 0 there, so we put another 0. And then we do the same as before. 32 plus 8 plus 2 equals 42. You might want to pause the video at this point, draw yourself out that table and have a go at this one, which is 110101. But remember, again, this is only a 6-bit binary number, so you might want to make sure that you format it with some leading zeros at the beginning. Converting the other way round from denary to binary, I think, is a little bit harder. The number we're going to try and convert back into binary is 43. We need to draw out the table like we see it there again. So we need to remember the number system. 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. But I think we only need 2 rows this time. And what we do with our decimal number, the 43, is we put that above the 128 over on the left hand side. And then we ask ourselves, does 128 fit inside 43? And the answer is no, so we put a 0. And then we carry the 43 over to the next one and we do the same check. Does 64 fit inside 43? The answer again is no, so we put a 0 and we carry it on to the next one. Now 32 does fit inside 43, so we put a 1. Where it gets a little bit complicated here is we're not going to be able to use 43 again when we're checking 16, because we've already used 32 of it by putting a 1 here. So what you need to do is work out the remainder of 43, take away 32, and we get 11. And we use 11 in our check this time. So does 16 fit inside 11? The answer is no. So we carry 11 over. Does 8 fit inside 11? Yes, it does. So this time we need the remainder when we're checking the 4. So we do 11 take away 8 to get 3. Does 4 fit inside 3? No, it doesn't. So we put 0. Carry the 3 over. Does 2 fit inside 3? Yes, it does. So we put a 1 and we calculate the remainder. 3 take away 2 is 1. Does 1 fit inside 1? Yes, it does. And we've filled all our boxes, so we've got our answer. 43 equals 0, 0, 1, 0, 1, 0, 1, 1. That's the values that's in the bottom row of our table. Now we might want to rewrite that without the leading zeros, because 1, 0, 1, 0, 1, 1 is the same as that answer. So that's how to work out from denary to binary. You might want to try another one. Now the maximum decimal number you might be asked to convert back into binary is probably 255, because that is the highest denary number that can be expressed with 8 bits of binary, i.e. if all of these boxes were filled with 1s, then the answer will be 255. But try this one for now. Draw out the table and try 212. Bye for now.